So this week we have Ian Miller, who's a coastal hazard specialist for Washington Sea Grant. And he's actually based on the Olympic Peninsula, and he works directly with stakeholder groups on the Olympic Peninsula, including fishermen, tribes, marine industries, etc. And I'm sure he'll be telling us more about his work during his talk. So I'll let you take it away, Ian.
All right, thank you so much. Thanks for having me, everybody, and joining online today. My name is Ian Miller, and I'm the Coastal Hazard Specialist is my title for Washington Sea Grant. And what I wanted to present about today was this analysis that I've just been involved with completing that attempts to quantitatively assess sea level rise vulnerability in Puget Sound using GIS-based tools and data. And my plan is to present at you or to you for about 35 minutes or so, but I want to leave plenty of time for discussion and questions at the end. And I'm actually very interested in getting your feedback on this project. So I've got a set of questions for you as well that I'll end with. But before I get there, Dr. Thompson asked me to add just a bit about Sea Grant, so I wanted to include that as well. For those of you that are unfamiliar with Sea Grant, we are a University of Washington-based program, and we do really two things. We fund marine research, so we have a biannual marine science grant program, and if you're unfamiliar with that, check it out, especially if you are faculty or a graduate student. And then we also have an engagement program or an extension, essentially an extension program that strives to connect communities with quote unquote the ivory tower, as I've kind of characterized it here in this conceptual model on the screen, really focused on marine and coastal issues, running the gamut from fisheries to aquaculture to marine water quality. And then I and a few others in our program focus on community coastal resilience to hazards. And that's something that Sea Grants have been working at now for maybe 15 years or so. I'm based in Port Angeles. Many of us are sort of not based out of the University of Washington, even though we are University of Washington staff. We are living and working in Washington's coastal communities. And there's probably about half of our staff, or near to half, that are distributed outside of the University of Washington campus. So that's a very cool aspect of our program and gives us insights about, certain aspects of community characteristics and community resilience that really benefit our program. So with that introduction, let me go back to the topic of the talk today. And I want to spend a bit of time sort of diving into a detailed motivation for our project. And I'm going to start here, referencing these two images on the screen here by noting that Washington State already deals with nagging chronic coastal hazards, including coastal erosion and coastal flooding. So the two photos on the screen here, both of these occur in Washington, and both, especially coastal flooding, are frequently the subject of coastal management decision-making, planning, and regulation. And both of these hazards, coastal erosion and coastal flooding, will be amplified by sea level rise, or the change in the average height of the surface of the Salish Sea and the Pacific Ocean, relevant to Washington, over time. And sea level rise is happening in Washington currently. So what you're seeing on the screen here is compiled from data collected at the 8 active tide gauges operating in coastal Washington. So this is observed water level information from Washington State. And in this case, what I've done is I've removed the vertical land movement signal from the tide gauges. I won't dive too deeply into that part of things, but just to try to get a sense for what, again, the sea surface is doing over time on average. And there's two lines on this plot. There's time down at the bottom. This is about a 70-year time series or so. And then this is the change in the average sea surface height in feet relative to basically our contemporary average sea level, technically the 1990 to 2010 average. And there's two lines on here. The thin one is the annual average. And then the dark black one is a 20-year rolling average. So that's the one that really is telling us what the long-term average sea surface height is doing. And you can see an upward trend there over that time period, roughly 4 inches of rise over this time frame. So sea level is rising in Washington. And sea level rise projections, or basically sort of the tools that we put together to try to assess what's possible in the future, like these that are on the screen that we published in 2018, also tell us that the rate of sea level rise is almost certain to accelerate in the coming decades. So these are, again, we've got time down on the y-axis, change in feet relative to our contemporary average. Here's that observed trend I showed you previously. And then all these lines are different projections across this probabilistic framework. Again, something that I'm not going to dive into in a great amount of detail, but is intended to span a range of uncertainty of possible future sea levels across a range of likelihoods. That's what these percentiles are. So again, the point is that many of these lines have an upward trend to the curve. There's an acceleration in sea level suggested by these projections. So this begs a large number of questions about how to address the coming challenges associated with sea level rise in Washington state, including perhaps most obviously where the impacts of sea level rise will occur. So, if we know that, then that maybe helps us to understand where should we direct our risk reduction effort now, where should we direct it to avoid future costs as sea level rises. So often the first thing we do when we're thinking about sea level rise impacts and future possibility is we make maps like this one. I'm guessing many of you have probably seen a map like this one at some point. This is an inundation, a sea level rise inundation map for the delta at the mouth of the Dungeness River, which is on the Strait of Juan de Fuca near where I live in Port Angeles. This is using what we call localized projections or relative sea level projections. And this map, there's these blue polygons that are intended to show us places that flood under different sea level rise and storm scenarios. And maps like this one, though, ultimately don't serve us perfectly in a planning and decision-making context because they focus only on exposure to a climate impact, in this case, flooding. To make many decisions, though, especially where resources are limited and prioritization is necessary, which is basically, the management world, then assessing what we call vulnerability to sea level rise related hazards is potentially a more powerful tool and concept. So the framework that you see on the screen is drawn from the IPCC, the Intergovernmental Panel on Climate Change, and it's intended to account for values and assets under the polygons on that exposure map that I showed you. So gets at, what's under those blue blobs on that map that we may value and care about. So there's three main elements to this vulnerability concept. First, exposure is the simple part. That's just, is the hazard there or not? What's the likelihood of that hazard? And this is effectively that map that I showed you on the previous screen. That is an exposure map. The concept of sensitivity, though, gets at what is under that inundation polygon on that previous map, and how the things that are under that polygon might be negatively affected by that exposure. So we can be interested in the sensitivity of really anything we value. Homes, roads, and utilities certainly are things that are frequently thought about in a sensitivity context, but also coastal habitats or culturally important landscapes, for example, can also be thought about in this sensitivity context. And then finally, this idea of adaptive capacity is intended to get at the ability of a system to adapt to those hazards and either reduce exposure or reduce sensitivity, sometimes via community characteristics, sometimes via individual characteristics of people that manage the landscape, sometimes associated with characteristics of habitats within the landscapes. So adaptive capacity is quite complex, or can be quite complex. The idea, though, ultimately, is to determine who or where may be most at risk. What is driving that potential negative outcomes that they may face, and where support of various types might be warranted or helpful. Again, if we have to deal with limited or prioritized resources, where should they go to achieve sort of the best bang for the buck, if you will? So at the scales that I've traditionally worked, this has been done mostly by getting local experts together around a set of exposure maps, sitting around a table, sort of talking and discussing, responding to questions, and trying to work out what's under those polygons, what do they care about, and what are the options for addressing the sort of assets that they find under the polygons on that map. And this working group may do some sort of semi-quantitative scoring on a table like the one on the screen. This is drawn from a climate vulnerability assessment for the North Olympic Peninsula that I was involved with, in which assets identified as exposed and important get a sensitivity and adaptive capacity ranking. So you can see, maybe you can see sensitivity on one axis of this table, adaptive capacity on the other, and then a bunch of assets in the middle that get ranked. And this approach can be very useful in that it can lead to a sense for shared priorities and direction in a climate planning process. But this approach also has a couple of key downsides. Notably, what you get out of a process like this is a function of the people in the room. So the process kind of has sort of natively low repeatability. It's also limited in terms of the spatial scale or the resolution that can be considered, as both are limited by the expertise or the local knowledge of the people in the room. And meanwhile, in the last 10 years or so, or longer, there's been this great flowering of various tools and analyses built around spatial data. And this led to a few of us to start to think about how the emergence of spatial data and tools could be leveraged to try to look at sea level rise vulnerability with fresh eyes. So just by way of example, there's two examples up on the screen here that are really spatial data-driven quantitative approaches for assessing things like flood risk. The First Street Foundation's flood factor is a score that's now assigned to every parcel in the country that tries to get at that parcel's flood risk. It's now something embedded in Zillow, so you can go look up the flood factor for the property that you live on. And then FEMA's National Risk Index is another that's intended to score every county in the country for its overall risk across all of the hazards that FEMA looks at and considers. So again, just as examples of this kind of like quantitative spatial data driven approach. So in 2020, I was part of a team along with Jim Johannesson and Avery Maverick from Coastal Geologic Services, which is a Bellingham-based coastal consulting firm. And we were funded with National Estuary Program money, so that's EPA funds, through the Habitat Strategic Initiative of the Puget Sound Partnership. So this was kind of part of the Puget Sound restoration endeavor, if you will, to develop a GIS-based approach for scoring sea level rise vulnerability that's intended to be used relatively. Or in other words, it's intended to identify those places in our study area, Puget Sound, where sea level rise vulnerability is highest. And we built the sort of concept around the key spatial unit, or at least what we think is the key spatial unit of decision making on the coast, which is the parcel, and configured our approach to account for both infrastructure sensitivity and habitat sensitivity, which is acknowledging the value of coastal habitats in Puget Sound as an ecosystem. So I'm going to use the rest of my time to dive a bit into our methods and then summarize very briefly our results. But again, we are interested in your thoughts on what we do next with this. So I'm actually doing a version of this kind of presentation primarily right now to as many what are called marine resources committees and local integrating organizations in Puget Sound. And I'm asking them the same set of 4 questions. And so I want to ask you all that same set of 4 questions as well. And I'm going to put them up on the screen at the end, but I'm going to walk through them right now. So the first thing I'm interested in is the analysis that I'm going to present to you here credible and transparent enough that it could have applications in planning and decision making? And if so, where should we make it available? And if the geodatabase were available, if essentially the spatial data that I'm going to show you were available, what sorts of training and communication tools should go along with it so that people know how to interpret it, know how to use it? And then finally, we do envision updates as sort of part of the process as new data becomes available. What are your suggestions for the best ways to make versions clear if it's published? So those 4 questions are going to be up on the screen at the end. Okay, so we ended up with 110,000 parcels in our study area, which is the box bounded in yellow on your screen. Like all data-driven projects, our approach was structured by the data available, which had a few important consequences. And there's a whole list of them, but just by way of example, our study area was constrained to the zone, again, bounded by yellow, because of the availability of elevation data that satisfied basically our project criteria. And this zone doesn't cover the entirety of Puget Sound as defined by the Puget Sound Partnership. And across this area, so I guess just to sort of be clear, what we don't include here is the central and western Strait of Juan de Fuca, which is unfortunate because this is the zone that I live in. But again, just one of the downsides of these data-driven approaches is that you have to have the data to be able to employ them. So that's something that we would like to include in a future iteration. Across this area, though, we quantified exposure to both flooding and erosion, and then also came up with an approach for scoring, again, the sensitivity of infrastructure and habitats on all these 110,000 parcels in this study area. So another important caveat at the start here is that we determined quickly that the concept of adaptive capacity is too complex and determined by, basically some unquantifiable community and individual behavior and resilience characteristics that we just couldn't attempt to quantify in our framework or within our project. As a consequence, our first pass quantitative vulnerability index becomes a more simple additive function of exposure and sensitivity on a parcel. So sort of this framework at the top here is the same as the one I showed you previously. In bold, vulnerability equals exposure plus sensitivity. But we've essentially are not including or considering that adaptive capacity element that I showed you in the IPCC framework at the start. However, we did, in the course of this project, enjoy a collaboration with a team from NOAA's NCOS, which stands for the National Centers for Coastal and Ocean Science. And they developed and just published a couple of weeks ago a community social vulnerability index for the Puget Sound watershed. And we are experimenting, or I guess have incorporated that in a way that I'll show you, not as a true measure of adaptive capacity, but rather as a modifier for our vulnerability score that we hope will represent where vulnerability is enhanced or lessened by various community characteristics. So this is primarily driven by census data. So these are really kind of big picture community characteristics that the social vulnerability index attempts to essentially quantify. And again, I'll touch on that at the end. But let me quickly go through the various method elements of our quantitative approach, starting with exposure. And again, we wanted to characterize both coastal flooding and erosion and represent how both may influence the hazard exposure of parcels through time. So coastal flooding we evaluated by measuring the percentage of each parcel inundated under each of 5 different sea level rise scenarios. And that was coupled equally with an assessment of the relative likelihood of erosion driven by wave climate and shoreline type and geology along Puget Sound shoreline. Note here that, again, as you know, we would have liked to incorporate an actual erosion model, something that tells you, hey, at this particular part of Puget Sound, here's how many feet of erosion we expect given a sea level rise scenario or projection. But no such thing exists for Puget Sound. And I mentioned that to illustrate, you know, that again, one of our key takeaways from a project like this one is that its applicability and the interpretation of results are limited by the availability of knowledge and data about the landscape. So again, just another data limitation sort of gets embedded in a data-driven project like this one. But despite that limitation, we still think that this approach gives us useful insights about present and future hazard exposure, and notably, by incorporating erosion, moves us beyond even our typical inundation-based erosion sea level rise maps that are the bread and butter at present for understanding sea level rise impacts, like the one I showed you from the Dungeness. So, but what I mean by that is that those are elevation-driven kind of bathtub model maps, whereas, and so for high elevation shorelines on Puget Sound, for example, those that are on high bluffs, like this little picture here at the lower left, those often, they don't show up as being exposed during, you know, if you're looking at sea level rise impacts, because the inundation maps don't inundate a parcel like that. It's too high. But when we attempt to consider erosion, parcels in places like this one shown in this photo suddenly pop out as having a sea level rise vulnerability. So I'm going to show you a few results figures that look like this map that I have up on the screen. So you'll see a couple that sort of look almost exactly like this, in which the relative scores are shown in color, scale bar down here at lower left, with light colors being low, in this case, exposure. And then we go up to this purple shade, that's the high exposure. But we've also highlighted the top 500 parcels in this kind of light blue color. And again, I'm just going to note this is probably hard to see on many of your screens, but this blue outlining is outlining the top 500 parcels in each category. Again, this is exposure. And this is a notably unsatisfying quick view of the results, but also conveys how the various vulnerability components are patterned on the landscape. And in this case, again, if you can sort of see the highlighting, we see our highest scores generally associated with places that are both low-lying and have a high erosion potential. So we see a lot of clustering of our highest scores in places on the shorelines with the largest fetches. So along the west side of Whidbey, for example, along the Strait of Juan de Fuca, places in the Sound that have large fetches, again, because of the sort of amplification associated with that erosion component. However, this is exposure. This doesn't care about what is on that parcel. So this is, again, just the exposure element. So let's get into the things that we care about. Again, this sensitivity component. So infrastructure sensitivity was calculated by evaluating how much of any structures on the parcel. And for this, we used Microsoft's building footprints data set, interacted with our 5 inundation scenarios. And we had small modifiers accounting for modeled flooding of agricultural lands or adjacent roads as a way of evaluating if accessibility to a parcel might be influenced by present or future flooding. So that modified the score a little bit. But another critical innovation in our view was the incorporation of a habitat sensitivity evaluation into our score as an equally weighted component of sensitivity. So here, what we decided to focus on was whether coastal habitats on that parcel would be able to migrate in response to sea level rise. And to do that, we leveraged NOAA's Marsh Migration Data Layer, which is available via NOAA's Sea Level Rise Viewer website, if any of you have ever seen or played around with that. And again, here, our interest was in acknowledging the value of coastal habitats regionally, and especially where, again, this was funded as kind of a restoration-oriented tool or data set. So again, where we may want to make decisions on vulnerability in an ecosystem restoration context, we felt like this would be really important. So again, we're sort of trying to look at infrastructure sensitivity, which is kind of a traditional thing to look at when you're thinking about something like sea level rise vulnerability or risk or hazard risk, but couple it with that habitat element. So again, something that's pretty distinctive and unique. So here, our highest scores for sensitivity are generally found, and again, same map view, but here we're looking at our sensitivity score, are generally found in the large river deltas in Puget Sound. So you can really see that pop out up here in North Sound. And these tend to be heavily developed, but also low-lying, and where agricultural lands are concentrated, and where in the marsh migration layer that NOAA publishes is elevation-based. So that suggests sea level rise would drive significant habitat migration. This, though, also highlights another important limitation of analyses like this and this one, which is that many of these deltas, like many others around the globe, are hydrodynamically controlled by dikes, tide gates, and other flow control sorts of infrastructure, which is generally poorly represented in elevation data sets and also poorly mapped. In our case, we relied on our elevation data set to represent expected future flooding, but know that there were errors in that elevation data set that led to unreasonable flooding in some situations where dikes weren't represented or tide gates maybe weren't represented. And so correcting or accounting for that in future analyses would essentially improve this kind of analysis that we've done here. Whoops, sorry, oh gosh. But again, despite that limitation, we think that we've still come up with an insightful way of assessing this rather esoteric concept like vulnerability spatially on the landscape. And when we do that and map the overall results, which I've done here, this is vulnerability, so exposure plus sensitivity. We see that despite the distinct patterns associated separately with exposure and sensitivity, we see a much more sort of a broader geographic distribution of vulnerability on the landscape, with some of our highest scores appearing in places where neither exposure or sensitivity was highest. So I'm using these red arrows to sort of point out a couple of places where this occurs. You know, in these locations in Hood Canal and South Sound, we didn't see exposure or sensitivity in that highest ranked zone. But when you couple them, we see these new spatial patterns pop out. So this illustrates the importance of thinking about the interaction of these two concepts when we're thinking about something like vulnerability. So we also find that overall, we think we've developed a potentially useful way of directing and prioritizing resources. So our highest possible score was 20, and these two pie charts show you the sort of the percentage of that 110,000 parcels that fall into different scoring bins from 1 all the way up to 20. And this pie chart is just pulling out the scores between 15 and 20. So the highest scores are pulled out here. And so what this suggests, so our highest possible score again was 20, and we find that less than 2,000 parcels overall out of more than 110,000 scored between 15 and 20. So this suggests that we can significantly decrease our vulnerability in Puget Sound by directing our effort at a relatively small number of parcels region-wide. And then finally, sort of heading towards the end, I want to revisit the integration of that community social vulnerability index that I briefly mentioned previously, again, developed by a team at NOAA's NCOS that we were working side by side with and that we're experimenting with incorporating. It's mapped here on the screen, kind of same overall concept as what I showed you previously. It's an index built primarily of census data. Again, this is published and available online. With the dark red colors here being the highest social vulnerability index scores and the lighter colors being lowest. And again, we aren't integrating this as a measure of adaptive capacity, but are attempting to use it to sort of investigate how certain community metrics, and again, this is talking about things at the large scale. We're not talking about individual characteristics of the people that own individual parcels, for example, but how certain community characteristics like census-driven things like income level, for example, may modify our assessment of vulnerability. And I'm not going to, again, dive into the nitty-gritty details of this index, but one approach that we're essentially working with is just to apply it as a multiplier to our vulnerability score. And when we do that, we see what we think is a realistic transfer of the highest vulnerability into new parts of Puget Sound. So for example, into urban estuaries in Puget Sound. So here, what I'm showing you on the screen is on the left, I know there's two maps here, a little bit hard to see, side-by-side views of Puget Sound. On the left is the vulnerability score that I showed you previously. This is our score. Again, just driven by sensitivity, exposure and sensitivity. And then on the right is with this social vulnerability index modifier. And what we see here are that these new places emerge as being in the top ranked socially modified vulnerability category. I'm pointing to them again with these red arrows in these urban estuaries in Puget Sound. And so again, we think that this is, potentially tells us something realistic and meaningful about vulnerability on the coastal landscape in Puget Sound. So just to sort of quickly illustrate the same thing for a place that possibly a little bit better, I pulled out zooms of results for King County. So I know some of you are not in King County, and so I'm making an assumption that many are, that at least maybe some of this coastal landscape a little bit better. So here is our vulnerability score distribution for King County. Hopefully you can make out here, this is Elliott Bay, Seattle, Bainbridge Island right here, just to orient you, and Vashon down here. So again, this is our vulnerability score distribution, with again, hot colors being the highest scores and the cooler colors being the lower scores. And then I can pull up right next to it our socially modified index right next to it. And so you can see, for example, a lot of these places, for example, in the lower Duwamish, sort of increase their ranking when we add this socially modified element, socially modified vulnerability index to the score. Whereas we see other places, for example, up here on Hood Canal at the upper left of the screen, where the socially modified score drops a little bit in some cases. Okay, so promise to get to the questions at the end, although hoping we have time for plenty of questions, because I'd love to hear your thoughts. But again, I just wanted to pull these questions back up on the screen in front of you, along with contact information and the required sort of funding statement and acknowledgement there. But these 4 questions I'd love to direct your thoughts to if you want to take the time, or I'm open to any other methods, questions, insights that you might have, etc. But with that, thank you so much. And Dr. Thompson, I don't know if what's the best way to go about doing questions?
Why don't